So yeah, we'll start looking at semiconductors today. So AC-DC behavior, like we've always talked about, our AC or alternating current changes direction. DC or direct current only flows in one direction, and we use rectifiers made from diodes to convert AC to DC. Cool. So reactance and phase angle. So we talked about previously, inductors and capacitors resist changes in current and voltage. This causes the phase shift, also known as our power factor, a foundation of understanding how diodes and other semiconductors interact with AC. Cool. Then we looked at power factor and polarity. So in AC circuits, current and voltage can lead or lag, whereas in DC circuits, which will move through towards rectifiers, current and voltage are in phase and unidirectional, so we don't get that phase shift. So what does a rectifier do in an AC circuit? Yeah, so basically it converts the alternating current into direct current by allowing current to only flow in one direction. So what happens to current and voltage when they are in phase? Yeah, you get a power factor of 1. Yep, we get resonance. What else? Yep, as part of the resonance, we get harmonics as well. So the main thing we know, as far as DC, they rise and fall together, meaning maximum efficiency and no reactive effects. But you guys have already mentioned it, in AC, if we have a power factor of 1 or voltage and current being in phase, there's also the chance of harmonics as well. Cool. So why might we want to convert AC to DC in an electrical circuit? Yeah, so our LEDs use DC, charging batteries. What else do you guys think? Yeah, if we only use DC, we're going to get no reactance. Yep. So the main reason we want to convert AC to DC, 12-volt things, is many electronic devices require that constant one-direction flow of current, or DC, for stable operation. So power supplies, control circuits, battery charging systems. So these ideas form the bridge between our electrical work and electronics. So we're moving from controlling energy flow mechanically or through magnetic fields to controlling it electronically using solid materials called semiconductors. So we'll move into semiconductor theory. So before we can understand how components like diodes, transistors, and SCRs work, we need to understand what they're made of. And if you guys remember back to year one, we did cover off a little bit about semiconductors and how they're made. So it's a material that doesn't conduct electricity as well as a metal, but it's not a full insulator either. So it conducts some of the time and some of the time it doesn't. What makes it special is that we can change how well it conducts by adding tiny amounts of other materials in a process called doping. So the most common semiconductor you'll come across is silicon. And so we'll have a look at what happens inside of it. Cool. So the atomic structure of silicon, it is in group 14 on the periodic table. So if you were to look at the periodic table, you would find it sitting in group 14. So each atom has 4 valence electrons in its outer shell. So when we're talking about the valence electrons, the valence shell is always the most outer shell of an atom. So in pure silicon, each atom shares its 4 valence electrons with neighboring atoms to form covalent bonds, which creates a stable crystal structure. So silicon in its normal state is a crystalline or crystal structure. So because all the outer electrons are tied up in these bonds, pure silicon is a poor conductor at room temperature. So think of each silicon atom as having 4 hands, and it holds hands with 4 neighbors. So everyone's hands are full. No one's got a free hand to give anyone. So no one's free to pass on the electrical baton or baton, if you want to call it that. That's why pure silicon doesn't conduct much electricity. So you can get silicon insulators. They do make good insulators, just like a lot of other natural materials. We can even use it to form solid insulators, because I'm sure a lot of you guys have seen that for a while they tried to make a lot of replacement products for metal out of silicon or other types of stone or silica-based products. Cool. So we'll move on. So this is what the atomic structure of silicon looks like. So if you can see the 4 valence electrons on the outside, you've got 2 at the top, 1 on the right, 1 on the bottom. So if it was next to another silicon atom or more silicon atoms, it wouldn't have any space in the outer shell. Cool. So doping. So to make silicon more useful, we add a tiny amount of another element called a dopant that changes how many free electrons it has available. So the process of making silicon conduct. So the first type we have is an N-type semiconductor. So before we move any further, does anyone want to guess what an N-type might be? Or does anyone remember what an N-type is? Yeah, negative. And what about it makes it negative? Okay, it's not quite. So remember that the electrons on the outside are considered to have it has free electrons, more electrons, because the electrons are considered negatively charged, whereas the nucleus with the protons in the middle is considered more positively charged. So it's created by adding a pentavalent element, so 5 valence electrons. So it has one more electron. It's a fancy term, but basically it's an element with 5 electrons, such as phosphorus or arsenic. So the extra electron becomes a free electron able to move through the crystal and carry a charge. The majority charge carriers are negative electrons. The remaining charge carriers, holes, are minority carriers. So it has one more electron. So if every atom has 4 hands and one new atom comes in with 5, the 5th hand has no one to hold. It's free to move. That's why we call it an N-type material. Then we move into a P-type semiconductor. So if an N-type has one more electron, a P-type will have pretty much will have one less electron. So it's created by adding a trivalent element or an element with 3 valence electrons, such as boron or gallium. So one bond is left incomplete. The missing electron is called a hole. Cool. The majority charge carriers are positive or holes, as electrons can jump from one hole to another. And this is basically a table looking at what they have in common, or the differences between them. So pure silicon is intrinsic. It has very few charge carriers, equal electrons and holes, and typical dopant, it doesn't have one. So it has a majority carriers of electrons in N-type and holes in P-type. So when they say majority, it means there's more free electrons than there are holes in an N-type, and in a P-type, there are more holes than free electrons. That's all we're talking about when we talk about the majority carriers. Before we move on, any questions on what we've covered so far? Cool. So when we're talking about the crystalline structure of silicon, this is what we mean by the crystalline structure. So as you can see, there's 2 electrons between each silicon atom. So it's one from if we look at the 2 on the left, the top and the bottom one each share one of their own electrons with the other, making a pair. So this would be a stable insulator because there's no free electrons to move and no holes for the electrons to fill. But then if we make something into an N-type semiconductor, so we've added a dopant, so we've added I can't remember what phosphorus. We've added a phosphorus atom into there. Now we have one extra electron. So we have a free electron to move throughout the silicon matrix. So we have created an N-type semiconductor. Then if we add a different dopant, so in this case boron, we leave a hole. So in this case, the majority carrier is the holes rather than the electrons. So that is what we would call a P-type semiconductor. Cool. So what happens to conductivity if we heat up pure silicon? Do you think we would get less conductivity if we heat up the silicon? What about everyone else? Will we get more less conductivity or more conductivity? So we've got 3 decrease, 1 more. 2 increase, 3 decrease. Oh, evenly split. So those who are saying it's increasing, why? And those who are saying decreasing, why? Why do you think it's going to increase or decrease? Oh, yeah. So Fergus thinks the electrons will have more energy to jump around. The negative tip coefficient. Resistance increases with heat. Thermal runaway. Breaks down and becomes inductive. Heat increases. Okay, cool. So some good discussion there. Cool. So it increases because as more electrons gain enough energy to break free from their bonds. So as we heat an atom, basically the vibration of the atoms increases. So as we heat the atoms actually start to move, and so the electrons gain more energy and can break away. Yeah, so it depends on the material. Sometimes, yes, temperature will increase resistance. Other times it will decrease it. All depends on the type of material. Cool. So which type of doping creates more free electrons, P or N? Okay, yeah, we seem to be in pretty much unanimous agreement there. Yep, so N-type. Yeah, so N-type creates free electrons. So what does the letter P stands for? Yep, we seem to be in pretty unanimous agreement there. Yep, P stands for positive because there are majority carriers are positive holes, or basically there is a lack of electrons, so there's a lack of negative charge. Cool. So bit of a summary. So semiconductors sit between conductors and insulators when it comes to conductivity. So depending on how we dope the material, they will either become conductive or non-conductive. So the process of doping, it either adds free electrons for the N-type or holes, so empty spaces for electrons to fill in the P-type. So the interaction between P and N materials forming the PN junction, which we're about to look at soon, is the basis for all semiconductor devices that follow. Cool. So I'll give you a chance to write these down. And does anyone have any questions before we move into the next section? Okay, no questions. So does anyone need a bit more time to quickly jot down those summary points? Okay, cool. So the PN junction and diode. So now that we know what P-type and N-type materials are, let's see what happens when we join them together. So the junction between the two types of material, called the PN junction, is the heart of every diode and most electronic components. It lets current flow easily in one direction, but blocks it in the other. So in other words, it acts like an electronic one-way valve. Cool. So the formation of the depletion layer. So if any of you guys have read through the learning resource, you've learned about the depletion layer. So when we get P-type and N-type materials, when we join them together, electrons from the N side diffuse across into the P side and fill the holes. This movement leaves behind immobile ions on each side, creating a thin insulating region called the depletion layer. So these immobile ions have less electrons and no holes. So the region has no free charge carriers. It acts like a barrier. Cool. The junction now has an internal electric field that resists further carrier movement. So kind of like that electric field in the capacitor, it resists further carrier movement. So imagine two crowds meeting at a doorway, one full of people, electrons, the other with empty spaces or the holes. They rush together and fill the doorway until it's blocked by those now stationary people. That's your depletion region. Basically, all of a sudden they've taken the rope away from the club and everyone's just going for a mad dash trying to get through the door. Or like when they open the gates at a rock concert or a stadium. Everyone rushes in trying to get through the small lines. And if anyone's tried to attend a All Blacks game or a big rugby game at Wellington Stadium or any of the ones out in the region, you'll know what I'm talking about. As soon as they open the gates for ticketing, smush or smash basically, as everyone mad dash tries to get in at the same time. So we have two types of operation for our diodes. The first one is forward bias. So forward bias is to make current flow. We forward bias the diode. So we connect the positive terminal of the battery to the P side or the positive side anode and the negative terminal to the N side cathode. So the external voltage pushes holes and electrons towards the junction, narrowing the depletion layer. So basically it pushes the holes and the electrons together, making the depletion layer even tinier. So once the applied voltage exceeds the threshold voltage, so 0.7 for silicon and 0.3 for germanium diodes, carriers cross the junction and current flows freely. So basically the holes are able to transfer over to the N-type and the electrons are able to flow through into the P-type, allowing for current flow, which then if we have a light emitting diode will give off light. Well, basically it allows current to flow freely. So this is what forward bias would look like. So we have our positive and negative sides of the battery. The negative is connected to the N-type semiconductor, and the positive is connected to the P-type semiconductor. So normally we talk about current flow in one direction, but if you think about the electrons are flowing out of the negative side through into the negative, the N-type semiconductor, and the holes are moving out of the positive side of the battery into the P-type material. And then because of that extra force, we're putting pressure on the PN junction until we get a breakdown or break over voltage, and then it conducts. Is this making sense to everyone? Just remember, when we talk about current flow, conventional current flow is positive to negative. Actual current flow is negative to positive, because remember, current flow is the flow of electrons, whereas conventional current flow is the flow of the holes. Cool. Cool. So yeah, the electron moves into the hole, and then the electron gets moved out again. So the hole replaces it. Cool. So then now that we have forward bias, we look at reverse bias. So we reverse the battery connection. So positive now goes to the N side and the negative to the P side. This pulls charge carriers away from the junction, which widens the depletion region. So we're pulling out the extra electrons in the holes, and we're leaving those depleted ions in the middle. There's going to be a lot of them. So our current drops to almost zero, leaving only the tiniest little bit of leakage current. The diode is now said to be blocking current flow. So if the reverse voltage becomes too high, though, the electric field can force electrons across. This is what we call breakdown, and can damage the diode unless it's designed to handle it, like a Zener diode. Basically, a Zener diode is designed to work a negative bias in order to keep voltage levels to a set voltage. So basically, your Zener diode, if it's set to have a breakover at 24 volts, as soon as we get above 24 volts, it'll allow current to go through, just to maintain voltage to a set level on the other side, which may be flowing to the load. Cool. So this is what it would look like. So the holes are moving to the outside of the P-type material, and the electrons are moving to the outside of the N-type material, thus increasing the depletion zone. So our depletion zone is widening because of the electrons moving out and the holes moving out. So please answer if this is making sense, or if it's not. It's going to be a lot easier if we get this understanding in now before we move on to the next parts of the topic. Cool. So the diode symbol and polarity. So for a diode, the anode connects to the P-type side of the material, and our cathode connects to the N-type. So remember, our anode is always the positive side, our cathode is always the negative side. So the arrow in the circuit symbol shows conventional current flow from positive to negative. And so this is what the symbol looks like. So we have a triangle and we have basically a line. So if you look at that as the direction, so the anode to cathode, so positive to negative, conventional current flow. So if you see this symbol in a circuit diagram, it means there is a diode installed. So for a diode, if we connect it in forward bias, the battery will allow current flow. Whereas if we connect it in reverse bias, we will get a bigger depletion layer. And so this is what we call its operating characteristics. So you see we've got the voltage and the current. As we increase the voltage in forward bias, the forward region, the current after it reaches the forward voltage, it increases quite rapidly. And then here we have reverse current leakage to the point where we have the breakdown voltage, where we get high levels of negative current. Yeah. We have the break over voltage on the right-hand side, or the forward voltage, and then we have the breakdown voltage on the reverse side. Cool. So which direction does conventional current flow through a forward-based diode? So in the diode, which direction does conventional current flow? So remember to always read what the question is asking. So it's referencing the diode. So what are we talking about in terms of the parts of the diode? Yep, so everyone's making reference to PN or negative positive. There we go. Yeah, so we're looking to have anode to cathode. So yes, it's positive to negative, but because they're asking us about the diode, it's from the anode to the cathode. So positive to negative, anode to cathode. Cool. So why doesn't current flow in reverse bias? This one is not asking you about the diode, it's just asking you about reverse bias. Yeah, Yep, so most of you guys are getting there. Cool. So because the depletion layer widens, preventing charge carriers from crossing the junction. So because we increase the depletion layer, because we're drawing the holes and electrons to the outside of the NP junction rather than pushing them towards the middle, we get a wider depletion zone. Yeah. Cool. What's the typical threshold voltage of a silicon diode? Yep, 0.7 volts. Cool. So, bit of a summary. So, joining p-type and n-type materials forms our p-n junction with a depletion layer in the middle. So, the diode conducts in one direction, forward bias, and blocks it in reverse bias. So, this one-way control of current is the foundation of rectifiers and all other semiconductor control devices. Cool. So get those notes down and we'll take a quick 3-minute break and I'll be right back. Okay, cool. So diodes in practice. So we've seen that a diode allows current to flow in only one direction, like an electrical check valve. So now we'll have a look at that behavior, how that behavior becomes incredibly useful in power supplies where we need DC from an AC source. So first we'll look at, so it's probably coming through a bit glitchy on the live stream, but so this is a half wave rectifier. So if you look at the circuit, we only have one diode. So it's allowing current to flow in one direction. But then when we get to the other half of the AC sine wave, it's basically being wasted. So we've effectively thrown away half of the waveform. So it's what we call pulsating DC. Good enough for simple users, but not very smooth. So this might be okay for charging a battery, but it's not going to be good for anything like a computer. So now the next one, we have a full wave rectifier circuit. So this time we're using 4 diodes. So any one time, 2 of the diodes are allowing current to flow through the positive and then to the negative. So the half wave circuit, the diode was like a one-way tap, only open half the time. In the bridge, we've built clever plumbing so water always flows in the same direction, no matter which way the pump turns. So again, it's still pulsating DC, but now we're using the full AC waveform, which again would be fine if you're just charging a battery, but it's not going to be any good for using any kind of electronics. So then we need to add smoothing. So again, sorry about the video, but as you can see, the orange line, which is the current actually flowing through our resistor or our load, we are actually getting steady DC because we've used a capacitor as a literal charge and discharge bank. We are getting a somewhat smooth DC current through our resistor. But you can see there that the spikes in the blue cable, it's going up and then down before it gets to the capacitor. And we're seeing the red and green waveforms are the AC going through our diodes. So why does the full wave rectifier deliver more DC than the half wave? Yeah, so it is using more diodes, but because it is using more diodes, it is using both halves of the AC waveform. So yes, it does contain more diodes, so there's more cost involved, but we get more benefit out of it. So what would happen if one diode in the bridge failed open? So one diode out of the four becomes open circuit, blows up. Yeah, intermittent, but more specifically, all of a sudden we don't have one of our diodes. What's happening to our waveform? So I did. So why do we add a capacitor across the output? The half wave output, loss of efficiency. Why do we need to add a capacitor? Yeah, so we add the capacitor for smoothing effects. So yeah, to try and create ripple-free DC. So it's to reduce voltage ripple and smooth out the DC output. You're never going to get 100% true ripple-free DC unless you do it from something like a battery source. That's really the only way you're going to get ripple-free DC. Cool. So brief summary before we move on to the next topic. So a diode can convert AC to pulsating DC. With the half wave, it only uses one diode. A full wave has four. It needs four to do it. So full wave rectifiers are more efficient, delivering continuous current in one direction. So if we add a capacitor, it smooths the output for steady supplies. So understanding these rectifier stages builds the foundation for SCRs, triacs, and transistor switching, which is what we're going to look at next. So I'll give you guys a couple seconds if anyone wants to write down notes. And just while you guys are doing that, just be aware when you do the assessment for this particular unit standard, they are wanting quite a bit of detail when it comes to answering the question. There are key points you need to cover over. I can't tell you exactly what those key points are, but there are specific key points that each answer needs to touch on. And so more detail is better than not enough. Just make sure it's detail that's on topic. So don't go into more detail than the question needs to answer it, but do not try and give a basic answer. Electronics does get quite complicated, and so therefore the answers to the assignment need to be more than just the basics. Cool. Does anyone need me to leave the slide, or shall we move on to the next part? Okay, cool. So now that we've looked at the basics of how a diode works and the p-n junction, we'll move into controlled semiconductors. So far, the diodes we've looked at could only do one thing, conduct or block, depending on polarity. But what if we wanted to choose when they start conducting? That's where controlled devices like SCRs or silicon controlled rectifiers, diodes, diodes for alternating current, and triacs, what we call a triode for alternating current, come in. So they work on the same basic p-n junction principles, but with extra control features. Cool. So some key points to cover before we get started. So reactive power inflates the total current drawn from the supply. Oh, what the? Okay. This is what happens when you make your PowerPoints at 3 in the morning. Cool. So first thing we're going to look at is the silicon controlled rectifier, or the SCR. So the basic structure and operation of an SCR. So it's basically a diode with a gate terminal. So we've added a gate or an extra leg to our diode. So internally, it's a 4-layer PN-PN device. So it has 3 junctions in it, 1, 2, and 3. The anode connects to the outer P layer, so the outer positive layer, and the cathode to the outer N layer. And the gate is connected to the inner P layer. So when forward biased, the SCR remains off, blocking current until a small trigger current is applied to the gate. Once triggered, the SCR conducts heavily and stays on until the current falls to 0. So think of it like a latching relay. So you give it a small push on the gate to start current flowing, and it stays on until the circuit naturally turns off. So it's basically a, kind of like a DOL starter. Once you push the start button, the contact retains itself until we remove the current flow entirely. Cool. So this is what it would look like. So you've got the symbol on the right is what you would see on a circuit diagram, whereas the one on the left represents the actual internal workings. So you've got the anode at the top, the cathode at the bottom, so still positive to negative, and then the gate. So basically a gate pulse, or a pulse to the gate, will enable current to flow in forward bias. But still only connects one way like a diode, so it's still only used for DC or for allowing AC to flow through it at certain times, or half the AC waveform. So as we apply the holes to P and the electrons to N, they will move towards the middle, but because the N in the middle is not, the P in the middle is not activated, it will not allow it to conduct. But once electron flows has started moving, then it will continue until we completely stop the current flow. So yeah, it is a latching relay type device. So any questions about the SCR? Okay, we'll move on. So some applications for this. So controlled rectifiers in DC motor speed control. So when we're using AC to power DC motors. Cool. So lamp dimmers and heater control circuits. Or over protection voltage, what's known as crowbar circuits. So we don't have enough time tonight to go through all of this. I'll just give you guys a heads up now. We're about halfway through all of the stuff we need to cover tonight. So now that we've looked at SCRs, or silicon controlled rectifiers, we'll look at diodes. So when we first look at a diode, it can seem a bit pointless. It's like a diode that works both ways. But that's exactly the point. The diode doesn't care about polarity, it cares about voltage. It stays off while the voltage across it is low. Then when the voltage builds up to a certain point, it suddenly breaks down and conducts sharply. That sudden switch on provides a strong short pulse of current. That's what makes it so useful for triggering other components like triacs, which we'll get into after this, which need a quick, definite pulse on their gate to turn on properly. So the structure of a diode. So it is a bidirectional device with a symmetrical PN-PN structure. It has two terminals only, and they are labeled MT1 and MT2, or A1 and A2. It does not have a cathode, and it does not have an anode because it is an AC device. So there is no gate terminal. The PN junctions are arranged so that the device behaves identically in both directions. Cool. So the operation. So at low voltage, the diode remains non-conductive, high resistance. As the AC waveform increases, voltage across the diode builds up until it reaches the breakover voltage, typically 30 volts. At that point, both inner junctions go into breakdown and the diode snaps on, conducting heavily and producing a sharp current pulse. As the current falls near zero again around the AC zero crossing, the diode resets and stops conducting, ready for the next half cycle. So think of it like a safety valve on a pressure tank. It doesn't leak gradually. It holds everything in until pressure reaches a set point, and then it suddenly releases it all at once and then closes again. The diode does the same thing with voltage. It pops open when the voltage builds up too high and then resets. Cool. So this diode makes sense to everyone. So does the operation make sense? Okay, good. Sweet. So why it's important. So triacs, which we'll look at soon, don't always trigger evenly or symmetrically if the gate signal is weak or delayed. So the diode ensures that every time the voltage builds up to the same level in either direction, it fires the triac at the same point in the AC cycle. This gives smooth dimming or consistent speed control without flicker or uneven waveforms. So if you fire a triac directly from a resistor and capacitor, you might trigger a bit earlier one half cycle than the other. The diode makes sure both sides behave the same. It waits until the voltage reaches its breakover point and then fires hard and fast, both positive and negative. So in both sides of the AC waveform. And then when we look at the structure of it, cool. So this is what the inside of it looks like. So you have A1 and A2, and it looks like two diodes next to each other because that's basically what it is. They've got a block on both sides and an arrow on both sides. So it is designed to work in both sides. And if you see on both sides, we have both a N-type and a P-type material, which allows for conducting in both ways. But again, it requires it to reach a certain voltage level before the pressure is enough. So it allows us to do things like this. So we'll look a bit more at this when we get to the triac, but as you can see there, this is basically the circuit for a leading edge dimmer. Is basically what this is. It's a leading edge dimmer for a lighting circuit. So what it allows us to do is control the triac like this. And again, we'll come back to this in a little sec, but just look at the waveform and kind of see what it is doing. Cool. So the typical value. So the breakover voltage is 28 to 32 volts. So the meaning of that is the voltage at which the diode starts conducting. So the holding current is 2 to 5 milliamps. So it is the minimum current to stay on. But if you notice, its reset voltage is 5 volts. So the voltage where it stops conducting is a lot lower than the breakover voltage. If you remember back to the circuit we were looking at before, it had a variable resistor in it. So using that variable resistor, we are changing the amount of voltage that will hit when the voltage will hit the diac, and therefore when it will start to conduct. So we can use it as a little bit of a timing device as well by changing the amount of voltage flowing to it. So everyone, I guess apart from maybe Aaron, did the simostat when we did block course. Yeah, so that variable resistor is doing the same thing as the simostat, but in reverse. Does that make sense? So instead of increasing the amount of time the AC waveform or the power is on, we're decreasing the amount of time that the diac is conducting, and therefore limiting the amount of the AC waveform that is going through. So that's how we use a diac and a triac to do dimming control with a electronic lights. But remember, we still need to buy an LED that is compatible with dimming. Always need to make sure you buy the LED that will actually dim. Otherwise, it'll just turn on and off. Or worse, flicker. Cool. So some applications. So when we pair it with triacs, we can use it in light dimmers, small heating controls, and ceiling fan regulators. And it provides symmetrical triggering and stable phase angle control. Cool. So why not just trigger the triac directly without the diac? So why do we not just trigger the triac directly without using the diac? Okay, so a couple answers there. So let sine wave build up, current voltage might be out of phase. Just inrush current. Yep, they do work together in cohesion. So basically, without the diac and its set voltage conditions, the triac would trigger unevenly, causing flicker or distortion of the sine wave. Cool. Nice, easy one. Does a diac care about polarity? Yep, it's a big no. So no, it fires equally in both directions once the voltage reaches its threshold. Cool. So what kind of voltage level does a diac typically need to conduct? Yep. So yeah, around 30 volts, 28 to 32. It depends on the type. Cool. So some summary notes. So the diac is a bidirectional trigger device that turns on suddenly when its breakover voltage is reached. So it provides consistent gate pulses for triacs or SCRs, ensuring symmetrical operation on both halves of the AC cycle. So without the diac, AC control circuits would suffer from uneven conduction and flicker. So those are the reasons why a diac is quite useful. Cool. So probably good to get at least those things written down if you are taking notes. Cool. So now that we've finished looking at diacs, we'll look a little bit more at triacs. They're known as triodes for alternating current. So we'll look at why it's called a triode in a little bit. Cool. So a triac is like two SCRs connected in opposite directions and sharing a single gate. Cool. So it can conduct current in both directions when triggered. So it is triggered by a small gate pulse applied at any point in the AC waveform. Once triggered, it conducts until the current naturally falls to zero at AC zero crossing. So if an SCR is a one-way electronic switch, the triac is a two-way switch. It controls power flow on both halves of the AC waveform. Cool. So we'll have a look at the physical construction. So it looks very similar to when we were looking at the SCR, the silicon controlled rectifier before. Sorry, so many terminologies. Got to keep them all straight. So the physical construction. So there we can see the PN-PN junction with the gate connected to the two internal P sections of the device on either side. Both connected in parallel, so we get less volt drop across them. Cool. And then we have the two thyristor analogy. So the thyristor is another word for the SCR. So you've got the two SCRs facing each way, connected by a single gate. And then when we bring them together in the circuit symbol, that's what we look for. So the two diodes looking each way with a gate added, which is connected to both sides of the diode, or both blocks. Cool. So, and then if we look at it in the circuit that we were looking at before, so we have our AC input and we have a resistor and a capacitor. So the capacitor is there for charging, but the resistor is there to limit voltage. So the arrow through it means it is a variable resistor. So as we move or rotate the dial on our dimmer, it increases and decreases the resistance, increasing it and decreasing the volt drop that's headed towards the diac rather than to being wasted in the resistor. That diac then conducts and sends the signal to the gate of the triac, allowing current to flow through the load. And if we look at the load waveform, you can see there it's starting to cut the leading edge of the waveform. And therefore we get a waveform out point like this. So you can see there the trigger point after T1, T2. So after time 1 and time 2, we get the triggering point, and that is when the diac conducts in both the positive and negative half. And there you've got the two holding currents, but if you look very closely on the other sides of the waveform, we have a small cutoff on the back edge of the triac waveform as well. That's that little 5-volt cutoff from the diac. So this is how we can use these two electronic components to dim circuits, which is why we need to make sure that we disconnect the dimmers before we do any insulation resistance testing, because they are not DC devices, but they are sensitive electronics. So it will not hit a transformer before it gets to these electronic components. That's why anything like a dimmer or electronic components that work on AC, we need to disconnect them. So LED downlights, we can AC IR test by shorting out phase neutral to earth, but we cannot do that with our electronic dimmers, mostly because they are not actually connected to the neutral. So we need to be aware of that when we are doing our testing. Cool. So the applications for our triacs, well, obviously we've been talking about it, are light dimmers, because we're limiting the overall amount of the AC waveform that is being delivered to our LED lights. We can use them for fan and motor speed controllers, because again, we're limiting the amount of the AC waveform that is being transmitted to them. And we can use them for heater and some power regulation circuits as well. Cool. So, does everyone have an understanding of what the triac is used for and how it operates? Or is there anything you need me to go over again? I will acknowledge it is a little bit of a dry, boring topic. I'm trying to make it as interesting as I can. You'll be glad to know, though, that the amount of night classes dedicated to electronics in this qualification is 1/5 of the nights allocated for electronics in the last qualification. So the last qual, they spent 5 weeks going over electronics. Okay, so a comparative summary. So our diodes are a PN junction. They are a one-way or a DC only operation. Control, they have no control method. Typical application is for rectifiers. SCR, or silicon controlled rectifier, is a PN-PN junction, or also known as a thyristor. It is a one-way device. Its control method is a gate trigger, and it is used for DC control and phase control. Whereas a diac is bidirectional, it conducts current in both ways, and its control method is its breakover voltage. And it is the typical application is used for triggering for triacs. And then we have our triacs, which are bidirectional. They allow current to conduct in both ways. Their control method is the gate trigger. So the typical application would be AC dimming and speed control. So this is the very basics of electronics. Obviously, there is a lot more detail we could go into, and there are a lot of different components. But this is the kind of stuff you need to know for the kind of everyday electrical work. So you're going to come across diodes and your rectifiers and your LEDs. Your SCRs are going to be used in DC control devices. Your diacs and triacs are going to be used for your AC dimming and speed control for things like your ceiling fans. Cool. So how is an SCR similar to a diode? Yep, so basically it conducts in one direction, but only when triggered by the gate. So yes, it's like a diode that only conducts in one direction, but it needs a trigger to the gate. So what does a diac do in a triac circuit? I like Aaron's answer, allows the symmetrical trigger. Yeah, so it provides a consistent triggering point by discharging into the gate of the triac. So yep, it provides a trigger for the triac, but it does it consistently, triggering at a predictable point at the predictable voltage level. So why does a triac make a better AC controller than an SCR? Yep, so basically it can conduct both ways, so it's perfect for AC waveforms, whereas the SCR can only do DC. Yeah, so yeah, SCR is great, but it's only for DC. So if we were going to use it, it would be for a full wave bridge rectifier when if we only wanted it to be conducting when the voltage is over a certain level, which I don't know why we would want that, but who knows? There's probably as far as it's the only use for it as far as yeah, DC. Unless we were using it in conjunction with a Zener diode to trigger a separate path. But we could get into the weeds with what we could use it for. I'm sure if you were to Google SCR circuit diagrams, you could find a whole bunch of different diagrams to try and figure out what they do. Cool. So in summary, so SCRs are controllable diodes that latch on after a gate pulse. Diacs trigger at a preset voltage, and they're often used to fire triacs. Triacs are bidirectional, letting us control AC power flow electronically. So these components are the foundation of modern dimmers, speed controllers, and power regulators. All right. That's what we've covered so far in this topic. And we just have one more section to go over. And now we're going to look at what are bipolar junction transistors, or BJTs. So far we've looked at devices that control current based on voltage direction, so diodes, SCRs, and triacs. Now we're going to meet a device that takes it one step further, one that controls a large current using a small current. So this is the transistor, and it's one of the most important electronic components ever to be made. Think of it as a little electronic tap or valve. A small flow of water or current at the handle controls a much larger flow through the pipe. So the basic construction, a bipolar junction transistor, I'll call it a BJT from now on, is made from 3 layers of semiconductor material. So we have 2 different types. We have a NPN, which is the most common, and a PNP. So that refers to the order of the types of doped materials or semiconductor materials and the way that they're stacked. So each transistor has 3 terminals. It has a base, or B, which controls, it's the control input. We have the collector, or C, which is the main current input. And then we have E, the emitter, which is the output where current leaves in a standard NPN transistor. So what I mean by that is, so this is what an NPN transistor looks like. Cool. So we have 3 terminals. We have the base, the emitter, and the collector. So it would normally be that the base is the middle prong, and the collector and emitter are the two on the outside. So NPN, not pointing in. So that's kind of a way to remember NPN, not pointing in. So in this case, the emitter is what we call the emitter, which is that the current is flowing out of it. So then if we will look at the PNP next to it, it's basically the opposite. So in this case, it is the emitter is the one that the current is flowing into, and the collector is where the current is flowing out to. So there isn't a, instead of a positive current flowing into the base, it is a negative current flowing into the base. So they just behave in opposite ways. Cool. So the internal structure. So it can be thought of as two diodes back to back. So one between base and emitter, and one between base and collector. So the base region is very thin and lightly doped. So only a small base current changes the charge distribution across the transistor and controls the larger collector current. So imagine the base as a tiny valve handle. Turning it slightly, or a small current, allows a big flow from collector to emitter. So no current in the base, no flow. Cool. So the operation. So to turn on, the base emitter junction must be forward biased, 0.7 volts. The collector base junction is reverse biased. So when base current, or IB, flows, it lets a much larger collector current, IC, flow through the device. The transistor stays on as long as the base current continues. So the base to emitter junction must be forward biased, whereas the collector base is reverse biased. Cool. So the relationship is roughly IC equals beta times IB, where beta is the gain, or factor at which the base current is multiplied. So the greater the gain, the more, basically the greater the current flowing in the collector. So if we increase the gain, we will get more current flow at the collector. Does that make sense? I don't want to get too far into the math of it, because all you really need to know is IC equals beta times I base. So you can kind of think as the base current being it's kind of like using a relay to switch a circuit, only instead of a simple on-off, we are using the relay as almost a current control device. So we can use it as a switch. So when the base current flows, the transistor is on. So the collector emitter acts like a closed switch. When we take away the base current, the transistor is off. So the collector emitter path opens. So that is a very basic way to look at it, is that the base is the switch between the collector and the emitter. Cool. So as an amplifier, so the small signal into the base produces a proportionally large signal at the collector. So it's proportional to the gain. So remember, as we increase the base current, it is multiplied by the gain, and that is how much current will flow from the collector to the emitter. So used in audio amplifiers and sensor circuits. So for this course, you only need to understand that the transistor can increase signal strength through current control. We're not expecting you to do anything further than that. You only need to understand that the transistor can increase signal strength through current control. Cool. So safe handling and testing. So static discharge can damage transistors. So when we're testing, use a multimeter's diode function. So you should see one diode reading from base to emitter, 0.6 to 0.7 volts. So one from base to collector, and open circuit in the reverse direction. Avoid measuring in circuit unless the power is off. But do not test live electronic equipment. Cool. So what happens if we don't supply any base current? Yeah. So basically we get no collector current flows. So the transistor stays off. So which terminal controls the transistor? Yep, it is the base. So the base is the terminal that controls the transistor. So what type of device is a transistor? Voltage controlled or current controlled? Yep, it is current control. Cool. So bit of a summary. So the BJT, it uses a small base current to control a large collector emitter current. So it uses a small base current to control a large collector to emitter current. Cool. So the two main types, NPN, arrow out, so flowing out of the emitter, and PNP, arrow in, flowing into the emitter. So it's used as electronic switches or amplifiers. So it can be used to switch or as a type of amplifier using the gain function. Cool. So it is the foundation device for modern electronics. Everything from relays to microchips evolved from it. So there is some videos online on YouTube if you want to take the time to go and watch it that talk about the origin of the modern transistor. Does anyone know what the first type of transistors were? Or what was before transistors? So we had transistor radios, but before we had transistors, electronics relied on vacuum tubes, also called valves. They were used as switches and amplifiers. So there's still some guys around who like to use vacuum tube amplifiers for live performances when so they're very popular with guitarists. A lot of them prefer the old valve or vacuum tube amps. There are still some modern electronic producers that still use them. They are considered slightly better, or I think the term they used to describe it was a warmer or brighter tone to them than the modern transistor or BJT type amplifiers. Cool. So we'll run a bit of a summary and recap. So come a long way today. So we've worked all our way from atoms to amplifiers. So we'll take a few minutes to pull the whole story together or look over everything. Everything we've looked at is built on the same foundation. When we join P-type and N-type materials, we get a P-N junction. And from that, we can create devices that either block, pass, or control current in increasingly sophisticated ways. Cool. So the basics. So silicon has 4 valence electrons, forming covalent bonds, and doping with pentavalent or N-type or trivalent P-type atoms changes conductivity by adding free electrons or holes. So the p-n junction in diodes creates a depletion region that allow one-way current flow, forward bias, conducting, reverse bias, blocking. The foundation of rectifiers that convert AC to DC. So remember, when we're talking about pents or pentavalent, it means 5. So penta, as in pentagon, 5 sides or 5 electrons. And trivalent, tri like a trident, or triple, meaning 3. So if you haven't got down any other notes, please get down these at least before I move on. Yeah, this is the basics. So silicon forms the semiconductors. Obviously, there is germanium diodes, but they are a lot more expensive simply because germanium is harder to come by. Silicon is pretty much everywhere around the world. Anyone need more time? Cool. So rectification circuit. So half wave, 1 diode uses 1/2 cycle. Full wave uses 4 diodes. It uses both halves, gives us a smoother DC, and then we add a capacitor for filtering and voltage smoothing. So controlled semiconductors, so SCR, one-way latching control via a gate pulse. Diac is a bidirectional trigger that fires at a fixed voltage at about 30 volts. A triac is a bidirectional controlled switch, kind of like 2 SCRs in opposite directions. All right, while people are getting notes down. So next week we have our end of term test, or basically, yeah, just our end of term test. So what will happen is I need to help another teacher administer a capstone, not your guys' capstone, but another one. So when you log in to the meeting, there will be the password waiting for you to do the end of term exam. So please stay on the Teams meeting while you do the assessment, and then once you've finished the assessment, post in the chat your percentage and then log off from there. I will still be doing attendance based on whether or not you log on and you post your percentage into the chat. So please make sure you do this. I will be checking afterwards. Okay, does anyone need me to leave it on the screen, or everyone ready to move on to the next page? More time? Cool. Remember, guys, you will not have your capstone until mid next year, just like you guys had it last year. And it will still be an in-person capstone mid next year. So you will have to go to the somewhere local. It will probably be the same place you did it, same place as last time that you did it. Cool. So our transistors, or our BJTs. So they have three layers: your emitter, your base, and your collector. So the small base current controls a large collector current. It acts as a switch or amplifier. So this is just an entry point into the wider transistor family. So you've got JFETs, MOSFETs, IGBTs, and so many more that we will not get into in this topic. We did used to cover off more of them in the previous qualification, but these are the ones that you need that are relevant to the qual that you're doing. Yeah, you're always going to have three legs with a BJT and most transistors. Okay, does anyone need more time? Okay, cool. So what happens to the depletion layer when a diode is forward biased? So in forward bias, it narrows, allowing charge carriers to cross the junction and current to flow. So if it's in forward bias, we have a narrower depletion range. In reverse bias, it widens. So why do we prefer a full wave rectifier over a half wave one? Cool. So it uses both halves of the AC waveform, giving a higher average DC and less ripple. So what does the DIAC do in AC control? Quite a switch as such, but yeah, it provides a consistent or symmetrical trigger voltage for a triac. So both halves of the waveform fire evenly. Cool. What must happen at the base of the NPN transistor before current can flow from collector to emitter? Yep. So the base emitter junction must be forward biased, so about 0.7 volts to allow base current, which then enables collector current. Cool. So in one sentence, how would you describe the purpose of a transistor? In one sentence, how would you describe the purpose of a transistor? Okay, so it is a device that uses a small input current to control a larger output current, acting as an electronic switch or amplifier. Cool, so all of these devices, diodes, SCRs, triacs, and transistors, are part of the same story, using semiconductor materials to control current flow. From here, we'll start seeing how these components are built into real-world circuits like power supplies, speed controllers, and electronic protection systems. So that is all of the learning material for tonight. So now that I'm on, let me just stop recording.